Welcome to the enigmatic universe where mysteries abound in the vast expanses of space. Today, we embark on a profound journey into one of the cosmos's most mysterious phenomena, black holes. A black hole is an area in space-time where gravity is so intense that nothing, including light and other electromagnetic waves, can muster the energy to escape it. According to Einstein's theory of general relativity, a sufficiently dense mass can bend space-time to create a black hole. The edge of no return is called the event horizon. While a black hole profoundly influences any object crossing it, it has no locally observable properties under general relativity. In numerous respects, a black hole behaves like a perfect black body, absorbing all light. Quantum field theory in curved spacetime suggests that event horizons emit Hawking radiation, mirroring the spectrum of a black body, with a temperature inversely related to its mass. For stellar black holes, this temperature is around billionths of a Kelvin, making it nearly undetectable. The concept of objects with gravity so strong that light couldn't escape them was first explored in the 18th century by Jean Michel and Pierre-Simon Laplace. In 1916, Carl Schwarzschild discovered the first modern solution to general relativity characterizing a black hole. The term black hole was first used in 1958 by David Finkelstein, describing a space region from which nothing can escape. Initially, black holes were considered a mathematical oddity, but by the 1960s, theoretical work confirmed they were a common prediction of general relativity. The discovery of neutron stars in 1967 by Jocelyn Bell Burnell heightened interest in collapsed objects as potential astrophysical entities. Cygnus X1, identified in 1971, was the first confirmed black hole. Stellar mass black holes form when massive stars collapse at the end of their life cycle. Once formed, black holes can grow by absorbing surrounding mass. Supermassive black holes, with millions of solar masses, may develop by engulfing stars and merging with other black holes, or by the direct collapse of gas clouds. Most galaxies are believed to host supermassive black holes at their centers. The presence of a black hole is inferred through its interactions with other matter and electromagnetic radiation such as visible light. Matter falling into a black hole can create an external accretion disk heated by friction, forming quasars, some of the universe's brightest objects. Stars passing too close to a supermassive black hole can be torn apart and shine brightly before being consumed. Orbits of nearby stars can be used to calculate the black hole's mass and location, helping to rule out other possibilities like neutron stars. Through such observations, astronomers have identified many stellar black hole candidates in binary systems and confirmed that the radio source, Sagittarius A at the Milky Way's center, is a supermassive black hole with about 4.3 million solar masses. The idea of a body so massive that even light could not escape it was briefly proposed by English clergyman John Michel in a 1784 letter. Michel assumed such a body might have the same density as the Sun, and calculated that a star 500 times the Sun's diameter would have a surface escape velocity exceeding the speed of light. He correctly noted that such massive, invisible dark stars might be detectable through their gravitational effects on nearby visible objects. Initially, the idea of giant but invisible dark stars was intriguing, but interest waned when the wave-like nature of light was discovered in the early 19th century. If light were a wave, it was unclear how gravity would affect it. In 1915, Albert Einstein formulated his theory of general relativity, showing that gravity does influence light's path. Shortly after, Carl Schwarzschild found a solution to Einstein's equations describing the gravitational field of a point mass. This solution showed peculiar behavior at what is now known as the Schwarzschild radius, initially thought to be a mathematical singularity. In 1924, Arthur Eddington demonstrated that the singularity disappeared with a change of coordinates. In 1933, Georges Lemaitre realized the singularity at the Schwarzschild radius was a non-physical coordinate singularity. Eddington noted that a star compressed to the Schwarzschild radius would exhibit such intense gravity that light could not escape. In 1931, Subramanian Chandrasekhar calculated that a non-rotating body of electron-degenerate matter above a certain mass limit, now called the Chandrasekhar limit, could not remain stable. Opposed by contemporaries, Chandrasekhar's ideas were partly correct. A slightly more massive white dwarf would collapse into a neutron star, which is stable. In 1939, Robert Oppenheimer and others predicted that neutron stars above another limit would collapse further, forming black holes. They suggested that at least some stars would collapse into black holes. with no physical law preventing it. In 1958, David Finkelstein described the Schwarzschild surface as an event horizon, extending Oppenheimer's results to include the viewpoint of in-falling observers. This period marked the beginning of the golden age of general relativity, with black holes becoming mainstream research topics. The discovery of pulsars by Jocelyn Bell Burnell in 1967, later identified as rotating neutron stars, spurred further interest in gravitationally collapsed objects. In this period, more general black hole solutions were found. Roy Kerr found the exact solution for a rotating black hole in 1963, and Ezra Newman discovered the axisymmetric solution for a rotating and electrically charged black hole in 1965. The no-hair theorem emerged, stating that a stationary black hole solution is described by three parameters: mass, angular momentum, and electric charge. Initially, it was thought that the strange features of black hole solutions were artifacts of symmetry conditions, but work by Roger Penrose and Stephen Hawking in the late 1960s showed that singularities appear generically in gravitational collapse. Penrose received half of the 2020 Nobel Prize in Physics for this work. In the early 1970s, the first black hole, Cygnus X1, was widely accepted based on observations. James Bardeen, Jacob Beekenstein, Brandon Carter, and Stephen Hawking formulated black hole thermodynamics, describing black holes' behavior analogously to thermodynamic laws. Hawking's 1974 discovery that black holes should radiate like a black body with a temperature proportional to their surface gravity was a major breakthrough. In 2016, the LIGO scientific collaboration announced the first direct detection of gravitational waves, representing the first observation of a black hole merger. In 2019, the first direct image of a black hole was published, based on observations by the Event Horizon Telescope. As of 2023, the closest known black hole, Gaia BH1, is about 1/560 light-years away. While only a few dozen black holes have been identified in the Milky Way, hundreds of millions are believed to exist, detectable only by gravitational lensing. John Michell used dark star in a 1783 letter, and early 20th century physicists referred to gravitationally collapsed objects. Science writer Marcia Bartusiak attributes the term black hole to physicist Robert H. Dicke, who likened it to the infamous Black Hole of Calcutta. The term appeared in print in 1963 and was popularized by John Wheeler in 1967 for its brevity and impact, though its exact origin remains unclear.